Okay, so let's get started from what we were discussing last time. Last time we were discussing about clock synchronization in a distributed real-time system, and we had said that there are two main types of synchronization that can be done. One is external clock synchronization, that is synchronized with respect to an external clock, and internal clock synchronization, where some internal clock values are used to synchronize the clocks. And then we had seen that the external clock synchronization is expensive, not used very commonly. And in the internal clock synchronization, we had seen two types. One is based on a master clock or a time server keeps on periodically transmitting its time, and the other clocks set their time. But that has the problem of single point failure. What if that node or that clock fails? So, a common implementation of clock synchronization is the distributed clock synchronization, where the clocks, they keep on transmitting their own values, and each clock averages and sets its own value. And then we had seen about the effect of bad clocks. Since bad clocks not very difficult to handle, they can be eliminated from computation, but the real difficulty was Byzantine clocks, which shows one value to one clock and another value to another clock. And then we are trying to derive some results on the impact of a Byzantine clock on the time value computed by all clocks. So, let us proceed from that point. So, we had said that a single Byzantine clock can make any two arbitrary clocks to differ by 3 epsilon by n second, where epsilon is the maximum permissible drift between two clocks. So, that we had seen a sketch of that proof by considering only 3 clocks, and then we are trying to show that due to a Byzantine clock, two clocks will differ by at most 3 epsilon time, and when they compute average, the average time will differ by 3 epsilon by n. And we said that, see, this is just a situation to explain the sketch of the proof rather than the proof itself, because with one Byzantine clock out of 3, we can't even keep them synchronized within any bound. And then we said that, see, if we understand 3 clocks, we can just add the other clocks, and because these are showing the same value to all other clocks, the sum of all their time values that is received by either C2 or C5 is a constant. It can be, we can consider that as m, and then we are trying to show that the value computed by C2, the sum of the clock values computed by C2 will be 3 C2 plus m by n, and that computed by C5 will be 3 C2 plus 3 epsilon plus m by n, and then they differ by 3 epsilon m. So, that is the proof. But if a single Byzantine clock can make two clocks differ by 3 epsilon m, then during this resynchronization interval, the 3 epsilon m by n should increase to epsilon, and then the resynchronization should occur, isn't it? We want to keep them synchronized within epsilon, and we know that they can differ by 3 epsilon m, we can't do anything about it. So, from 3 epsilon m by n to epsilon, we can allow them to diverge, and then we need to resynchronize. See, earlier we are trying to resynchronize from 0 to epsilon, isn't it? M is the number of Byzantine clocks, yes. So, 3 epsilon by n is the time value that a single Byzantine clock will make two clocks differ by, and m is the number of Byzantine clocks. So, the total time difference due to m Byzantine clocks will be 3 epsilon m by n. So, we can set 2 delta t rho is equal to n epsilon minus 3 epsilon m by n. So, that is basically epsilon minus 3 epsilon m by n, or delta t is equal to n epsilon minus 3 epsilon m by 2 n rho. So, this is the idea here. See, the time values by themselves differ from they differ by 3 epsilon m by n, right. We can't do much about it. So, from 3 epsilon, okay, I should not have drawn it here, actually I should have drawn it here. So, I done a mistake here, see, or maybe I should have drawn 3 epsilon m by n here and epsilon here. So, in any way 3 epsilon m by n, they will differ due to presence of Byzantine clocks. So, from 3 epsilon m by n, so this I should have brought here. So, from 3 epsilon m by n to increase to epsilon, by the time they increase to epsilon, we should resynchronize, right. Or in other words, epsilon minus 3 epsilon m by n is the divergence that we can allow between clocks within the delta t interval. So, in delta t interval, the divergence will be 2 rho delta t, that we know. So, 2 rho delta t will be epsilon minus 3 epsilon m by n. So, this diagram is a bit wrong, I have drawn it wrongly. We should have it 3 epsilon m by n some, okay, if this is the 3 epsilon m by n, then this should have shifted here. So, because we have to synchronize as soon as their difference, their drift is equal to epsilon. So, we have to compute how much time they take to drift from 3 epsilon m by n to epsilon. So, that is basically the permissible drift is epsilon minus 3 epsilon m by n, which is n epsilon minus 3 epsilon m by n, which should be equal to the drift that is possible due to rho, that is 2 delta rho. One might be drifting in the positive side and another might be drifting in the negative side. So, the total drift in delta t will be 2 delta t rho, or delta t is equal to n epsilon minus 3 epsilon m by 2 n rho. But we know that n is equal to 3 m plus 1, because less than 1/3 of the clocks are Byzantine, and therefore, delta t is equal to 3 m plus 1 epsilon minus 3 epsilon m by 2 n rho. So, we can take out this 3 m epsilon here. So, it will leave us with epsilon by 2 n rho. Is that okay? So, in the presence of Byzantine clocks, m Byzantine clocks, where m is less than 1/3 of n, then we need to resynchronize after every epsilon by 2 n rho.
But this delta t is independent of m.
Okay, yeah, see, he is asking that delta t is independent of m. So, does anybody have any answer to that question? So, he says that delta t that we have computed, that is the frequency of resynchronization, is independent of m. It has become independent of m. Why is that?
Because we have considered average, the maximum possible.
Yeah, exactly. So, we are assuming that any number of clocks between 0 to m can be Byzantine. At best, if there are m Byzantine clocks, we can keep them synchronized. At best, there are m Byzantine clocks, we can keep them resynchronized by transmitting within epsilon by 2 n rho. Of course, if you had no Byzantine clocks, or let us say just 1 or 2 Byzantine clocks, then your resynchronization interval can be longer, isn't it? This is the worst case.
So, can say even if all the n are Byzantine, still we can keep it synchronized.
No.
From this expression.
See, this is the assumption that is given, n is equal to 3m plus 1. Under that assumption we have substituted here n is equal to 3m plus 1. But given that n is equal to 3m or n is equal to m, let us say n is equal to m if you make it. So, m minus 3 epsilon m by 2 n rho. So, that will become minus 2 epsilon by 2 n rho, which is a impossible period for resynchronization, right. So, here this expression says that as long as the number of Byzantine clocks is less than 1/3, you can keep them synchronized by transmitting, by every clock transmitting its clock value every epsilon by 2 n rho time units. Looks okay? Yes.
So can we, in the previous class you had said that like at least no more than 1/3 if it is bad or Byzantine, then only you can keep
Yes,
it
yes.
So can we derive this statement from this expression? Like
Of course, yeah, of course. So, maybe that is a thing that to think about. See, what he says is that we had claimed to start with without any proof, saying that if less than 1/3 clocks are Byzantine, then we can keep them synchronized to any bound. If more than 1/3, if 3 out of 9 are Byzantine, we can't even keep them synchronized to any given bound, whether you tell 10 second or whatever, we can't keep them synchronized. So, what he says that this can be the basis on which you can claim. See, that time we just stated that, see, 1/3, less than 1/3 should be Byzantine for us to keep them synchronized within any bound. So, this may be the basis on which we can show that, see, if more than 1/3 is Byzantine, then we can't keep them synchronized. The retransmission period will be impossible to meet, that is negative, right. Okay. So, let us look at an example. A distributed real time system has 10 clocks, and given that up to 3 clocks are Byzantine and the maximum drift is to be kept less than 1 millisecond, and the clock manufacturer has specified the drift rate between 2 clocks is 5 into 10 to the power minus 6. Determine the resynchronization interval. Okay. So, this is simple. Know the expression delta t is epsilon 2 n rho, 2 and 10 is the number of clocks, 5 into 10 to the power minus 6 is the drift rate, and 1 millisecond is the maximum drift permissible, and then delta t is 10 second. So, as long as less than 3 clocks are Byzantine, less than or equal to 3 clocks are Byzantine, then as long as the time values are broadcast by every clock in every 10 second, then the clocks will become synchronized. But what if we know that no clock is Byzantine? How do we do that? What is the synchronization interval? Okay, okay, we can. Earlier we had asked, we were set 2 rho delta t. That is what he says. The 2 rho delta t is the time we took for the clock to diverge from 3 epsilon m by n to epsilon. Says that now we need to equate that to 0 to epsilon, right. Okay, simple thing. Now, let us look at another problem. So, this please try to do it. So, we have a distributed real time system with 12 clocks. The clocks are required to be synchronized within 1 millisecond of each other. At best, 2 clocks in the system are Byzantine. We know that at best 2 can become Byzantine, and the maximum drift rate is 6 into 10 to the power minus 6. Now find the rate at which the clocks need to exchange their time values, and also the total number of message exchanges required per hour for synchronization of the clocks. So here at best means it can be 0 clock can be Byzantine, 1 clock can be Byzantine, or 2 clocks can be Byzantine. And we know that as long as less than 3 clocks are Byzantine, they can be kept synchronized. It is less than 1/3. So less than 3 clocks, up to 3 clocks they can be kept synchronized. So please try.
Actually, here we should not take the last expression. We should take the at best 2. So
Yeah, at best 2. So if you compute assuming that less than 1/3, that is 3, then your resynchronization interval will be much smaller. It will be smaller than what it should be actually. So this is the additional fact that is given, that at best 2 clocks are Byzantine. So please try to do this. Don't assume that up to 3 clocks will be Byzantine, because this is additional fact here. So we need to compute the effect of 1 Byzantine clock. That is the most crucial step or crucial result. If we know that, we can do that easily. That is, what is the impact of 1 Byzantine clock on all clocks in the system. And then we can easily show that what will happen if there are 2 clocks are Byzantine. So, okay, one person has completed. Anyone else has completed? Okay, some 2-3 persons have completed. So need the result of one of you, so that you can display that. Nothing very difficult, isn't it? So why are you taking so much time? We know the result for 1 clock, 1 Byzantine clock. How does it impact all other clocks? So 2 clocks, what will be its impact on the other clocks? And then the drift should be between that value, the impact of 2 clocks, because beyond that we can't keep them synchronized. So from that point until the increase to epsilon, which is given to be 1 millisecond, that should be equal to the drift that is possible under the specification, that the drift rate is 6 into 10 to the power minus 6. So that should be 1 millisecond minus 2 into epsilon, which is 1 millisecond by n is 12. So, 1 millisecond minus 2 epsilon by 12.
So we can use that expression, 2 rho delta t equals to n epsilon minus 3 epsilon n.
No, you do whatever we need the result. You do whatever. What I am saying is that do not assume 3
Yes.
as the Byzantine, assume 2 Byzantine clocks is given.
Then 10 to the power 3 by 24.
Yes.
So, okay, so need a answer, we will display that. Okay. So, your name is what? Manoj. Okay, let us look at the answer of Manoj. So, let them focus here. So, are you able to see this? Okay. So, looks very faint anyway. So, we have 2 rho delta t is n epsilon minus 3 epsilon m. Why 3 epsilon m?
3. One clock, one Byzantine clock will have 3 epsilon by n. So,
Acha, 3 epsilon m. M is
With the
okay, number of Byzantine. Okay. So, each epsilon will have 3 epsilon by m, 3 epsilon by n as the impact on other clocks. So, the time for a clock to diverge from 3 epsilon to 2 by n, 2 epsilon will be epsilon minus 2 into 3 epsilon by m, sorry n, which is 12, is not it? Which is equal to 12 epsilon minus 6 epsilon by 12, which is equal to 6 epsilon by 12, which is epsilon by 2, is not it? So, epsilon by 2 should be equal to 2 rho delta t. So, based on that he has done it and got 1 by 2 into 10 to the power 1 by 24, is it? 1 by 24. So, 2 rho delta t should be equal to epsilon by 2, or delta t should be equal to epsilon by 2 rho, sorry 4 rho. Delta t should be equal to epsilon by 4 rho, right? Okay. So, is that okay with everybody? Okay, let us proceed from that point. Let me see if I had computed that or not. Okay, I think I have computed here. So, time difference due to 2 Byzantine clocks is 3 into epsilon into 2 by n, and resynchronization is needed. So, this is equal to 6 epsilon by n, and resynchronization is needed when the clocks diverge by epsilon minus 6 epsilon by n, which is n epsilon minus 6 epsilon by n, right, or 2 delta t rho is equal to n epsilon minus 6 epsilon by n, or delta t is equal to 10 to the power minus 3 by 4 into 6 to the power minus 6 is equal to 41.67. Just check what is the value we are getting. 41.67 second. Now, what about the message overhead? Per hour, how many times the clock value needs to be transmitted? Each node would transmit n minus 1 messages per resynchronization interval. there are 12 nodes, so it will send 11 messages. Each node will send 11 messages per resynchronization interval, and we know that the resynchronization interval is 41.6 or something. So, each node sends n minus 1 and there are 12 nodes. So, 12 into 11 will be 132. So, per resynchronization interval 132 messages need to be transmitted, and we know that there are every 41.67 second one round of transmission should occur. So, that should be 60 into 60, that many seconds are there in an hour, divided by 40.67 is 86.41, and in each of these retransmission, each of these 86.41 retransmissions, 132 messages are sent. So, the total you will find some 11,406. Now, just a small variation of that problem. No clock is Byzantine. See, same problem actually. Distributed system has 12 clocks, maximum drift is to be kept within 1 millisecond. No clock is Byzantine, but 2 are defective. Maximum clock rate is 6 into 10 to the power minus 6. Message transmission latency is 50 into 10 to the, okay, here there is another factor given here, just check here. Not only that we have no Byzantine clocks and 2 are defective or bad clocks, we have a message transmission latency also given. Find the maximum resynchronization period in the centralized scheme and the distributed scheme. So, first do for the centralized scheme, what is the maximum resynchronization period? And then we need to do for the distributed scheme. So, are you able to make progress on this? I mean, how will you do? First, let us find out how will you do the centralized scheme. Under this data, that 2 are defective, no Byzantine, and the message transmission latency is 50 into 10 to the power minus 6. A constant message latency is assumed here between any 2 clocks, 50 into 10 to the power minus 6. We need to keep all the clocks synchronized within 1 millisecond. Okay. Yes. See, all the clocks are to be kept resynchronized even with respect to the master. So, the actual drift that is allowed is 1 minus this value. This becomes more than that, is it? No, that is okay. So, this is microsecond anyway. So, it should be 1 to 10 to the power minus 3 minus 15 to 10 to the power minus 6, right. That is the maximum drift that is permitted, and then the resynchronization should occur, is not it? So, how much time does it take to drift from 10 to the power minus 3 minus 50 minus 10 to the power 6 to 10 to the power minus 3. So, the drift should be between, say we can't keep them resynchronized within 50 into 10 to the power 50 into 10 to the power minus 6. Of course, we can deduct that time value and keep it with synchronized with respect to master. That is a different scheme, right, since we know this to be constant. See, if we know that this is constant, we can deduct that from the time value received from the master and then set that time value, right. But let us assume that this is just a bound. We do not know whether it will be 0 or 1 or 0 into 10 to the power minus 6 or 1 into 10 to the power minus 6. It is not constant, let us assume. And then we can't keep the clocks synchronized with respect to the master any finer than 50 into 10 to the power minus 6, right, any less than 50 into 10 to the power 6. We can't keep them synchronized because the time value can be anything between 0 to 50 to the 10 to the power minus 6, and this is 10 to the power minus 3. So, by the time the time diverges to this one, should have a resynchronization, right. So, how much over what duration delta t will this divergence from 50 into 10 to the power minus 6 to 10 to the power minus 3 will occur. So, that should be the answer.
195 degrees.
Okay. So, please that may not be very difficult now to do, but what about the distributed scheme? In a distributed scheme, no clock is Byzantine, 2 are defective. So, 2 defective means 2 time values are simply ignored, it will be 10. So, the number of clocks becomes 10 because 2 are defective. Now, the transmission latency is given. Now, if it is again not a constant latency, it is a bound. So, instead of the Byzantine, see, in the presence of Byzantine clocks, we said that, see, we can't keep the clock synchronized any less than 3 epsilon m by n, but here we can't keep them synchronized any less than 50 into 10 to the power minus 6, right. So, based on that, the divergence from 50 into 10 to the power minus 6 to 1 millisecond, that is 10 to the power minus 3, again we need to do the computation. So, please try that. Let me see if I have solution there. No, I do not have the solution here. So, please try that. Can't really give you too much time to compute that. Please try that at your home, and if you are difficult, we will discuss in the next class. Nothing very difficult actually. See, here we have a, see, if we had a constant latency there, if you had a constant latency, then
The resynchronization period would be the same for the centralized and same for the distributed.
okay. So he says that it will be the same. See, if we had the constant message transmission latency, then we would not be impacted at all, because every clock will basically subtract this from the time value received, because it has taken this much time to come, right, 15 10 to the minus 6. So, the time value is older than this one, or it should have been sent earlier by this time. So, what it will do is, sorry, it will not subtract, it will add this time value, isn't it? The present time value at that clock will be the time value received plus 50 into 10 to the power minus 6, if it was a constant latency. But if it is just a bound that is given, that it can be no more delayed than 50 into 10 to the power minus 6, then the delay can be 0 in 10 to the power minus 6 or 1 in 10 to the whatever, right. So, up to 10 to the power minus 6, and then need to take that into account.
Actually, this message transmission latency means when the clock sends the message, its time value.
Yes.
That maximum delay can be that.
Maximum delay, exactly.
So, what this comes is we have to find the delta t normally and subtract this value from that delta t.
No. See, what we are saying is that the delta t is the time after which resynchronization occurs, right? And by that time the clocks have drifted up to epsilon. Now, but initially itself, let us assume that the initial difference between clocks is not 0. See, after, even if you resynchronize, the difference can be up to this latency. The difference can be up to the latency. See, if we know that the latency is L, then we can set minus L, but we do not know, it can be 0 to L, the message transmission latency.
So is it not like this? If we calculate delta t normally,
Yes,
and send the time, we not consider the message latency previously.
yes.
Now only the extra thing is that the latency is there. So we'll take that latency into account and transmit before that much period.
How do you compute delta t?
Like delta t minus
Normally we
delta
used to compute.
I mean, without assuming the
Without
latency.
assuming that latency and
Yes.
subtract this value from the delta t. We get
Not really, because there in computing delta t, you are assuming that the clocks are all synchronized, right. So, starting with total synchrony, they were diverging up to epsilon, but here we are saying that the clocks can be different from each other by some amount. It is not 0 to delta t. So, we need to resynchronize them more frequently than delta t.
That's what he is saying.
we can subtract this value from the delta t.
Suppose normally
Yes.
it is synchronized,
Yes.
then we transmit every delta t.
So, you are saying that if it is, let us say 20 second, and let us say the message transmission time is, let us say some microsecond, you will just subtract a microsecond, is it?
Yes.
No, just check it out.
That much earlier if we send it.
So by that time it will reach the
May not be that value, because this is the time for the clocks to diverge. It is not that from that value you subtract, and I do not think so. Please.
That limit, before the diverge to that limit, we will transmit it by that.
No, see, the transmission frequency may be 20 second, right? That is the clock transmission, and here the message transmission delay is of the order of few microseconds. So, you just subtracting few microsecond from 20 second may not be much different, isn't it?
So that transmission period we have computed considering the case that the clocks will not diverge beyond certain limit.
Okay.
So that is already taken into consideration. Now if we take into consideration the latency also, that much we will subtract from the period.
Okay, please think about it. You think about it, that whether, see, the argument that I am giving you is that, see, the clocks are synchronized to start with, then you can transmit a delta t, and then you can keep them synchronized. But here the clocks to start with are not synchronized by some amount. So, they have to diverge.
after every interval we are making it then synchronized.
No, just think about it. I am just telling you, think about it, tell me in the next class, right. Okay, let us proceed. So, let me just ask few questions now that we have computed, we have completed our discussion on clock synchronization and also the scheduling that we had computed last time, we discussed last time, and I did not ask you any questions. So, why is it that algorithms used for scheduling on multiprocessors are not satisfactory for distributed systems?
Those synchronization between the clocks.
Any other answer?
Multiprocessor system can be at same geographical location, whereas distributed.
I mean, how does that impact the scheduling algorithm? Task scheduling, how will it impact, whether they are at the same location or at different location?
Message transmission overhead.
Okay, message transmission overhead. So, we have to consider that in the scheduling, but see, if it is static, then there is no overhead, isn't it?
Then
If it is
again,
only
order
dynamic.
process events.
If it is dynamic tasks, then there is a, but any other
The
thing that
ordering of the events also.
I mean, did we consider the ordering of events anywhere during our scheduling algorithms for distributed and multiprocessor system? Anyone wants to answer anything? Yes, any other answer?
Simultaneously, we need to keep track of all the tasks at different systems, the deadlines, only single system thing is always.
Okay. Okay. See, in a distributed system, we don't have a knowledge of the global status, right? We can't have actually. So, in a multiprocessor system, we have that, and therefore, we can have a better scheduling algorithm, easier, I mean, more efficient algorithm in a multiprocessor system than a distributed system. As far as the static scheduling is concerned, there is no difference, like he said, because we know the status and each node just runs some tasks. Of course, if we consider the communication between the tasks, then there may be a difference, but as long as these are static tasks running at different nodes, there is no difference between a multiprocessor and distributed system. Only with respect to dynamic transfer of tasks, whether it can transfer to some node and what is the cost of transfer, time taken to transfer, and the global knowledge of the status of various nodes. So, that will make the difference. So, that is the main reason why we can't use a distributed task scheduling algorithm in a multiprocessor and vice versa. Okay. Now, in external clock synchronization scheme, how can Byzantine clocks be handled?
Byzantine clocks don't have any meaning.
Okay, right. So, see, he has understood it fully. He says that, see, Byzantine clocks are the clocks of the system, right? The external clock is not Byzantine. So, the external clock just keeps on transmitting, and whatever be the clock, it just sets its own value. Byzantine has no meaning, that is what he said, correct. Okay, I think this is just argued out there, that how do you show that if there are n clocks in a distributed system and m are known to be Byzantine, where 3m plus 1 is greater than n. So, that is more than 1/3 is Byzantine, then the clocks cannot be resynchronized within any predefined bounds. So, that I think we need not discuss now, because he has already argued out that see, if we try to keep them synchronized using the scheme that we discussed, internal clock synchronization, then we need to retransmit or resynchronize them with negative frequency. Okay, now, since we have discussed about the basics of scheduling in a uniprocessor, multiprocessor and distributed systems, and we looked at the clock synchronization, let us look at the real-time operating systems. First, let us look at some very basic requirements of a real-time operating system. The first thing is a real-time priority. We will see what do we mean by a real-time priority. Then what kind of scheduling policy is supported. So, these two are important factors that a real-time operating system must support. One is that it must support real-time priority levels, and the kind of scheduling policy to be supported, memory locking support. See, why we need a memory locking? Need timers, interrupt handling, I mean different from what we have been discussing in traditional operating system. Special file system support called as real-time file system, special arrangement for device interfacing. But first, let us look at what do we mean by real-time priority level. Actually, a real-time priority level, which we will also call a static priority level, here the operating system does not change the programmer assigned priority value of a task. Once a programmer sets a time value, priority value for a task, then it just continues to remain that throughout the execution of the task. But the traditional operating systems, Unix, Windows or whatever, they all, once the programmer assigns a time priority value, they keep on changing the priority value of the task. Why do they do that? It is a very fundamental question in any operating system discussion, that why a operating system needs to change the priority value of a task. We will see, we will discuss little further here, because normally not discussed in a first level operating system course, that why a operating system needs to change the priority of a task as it executes. We will see that the answer is to maximize the throughput. We will also give a formula they use to compute the priority dynamically, that is both Windows and Unix and all other operating systems. Another requirement for a real time operating system will be the task preemption time. For a real time operating system, we need a preemption time which is less than a few microseconds. But we will see that the worst case preemption time of the traditional operating systems like Unix or Windows is of the order of a second. We will see that this is caused by this large difference in the preemption time is caused by a non-preemptive kernel. We will see that what is this non-preemptive kernel of a traditional operating system and why it is non-preemptive to start with. But what do you mean by task preemption time? Yes, anybody would like to?
Context and all has to be saved, and so that time.
Okay. So we were discussing a priority driven preemptive scheduling mechanism. So under some events, the current task must be preempted. So after determining that the current task will be preempted, how much time does it take to actually do the preemption? We will see that in traditional operating system, we need a large preemption time, because the kernel is preemptible. Once it is in the kernel mode, you have to wait until it comes out of that. And even the user program, it can go into a kernel mode, right? Do you agree with that? How will it go into kernel mode? System calls, exactly. So the interrupt latency is the time delay between the occurrence of an interrupt and the running of the corresponding interrupt service routine. So in real time systems, you will see that various types of devices, sensors and actuators, they give interrupts, and once the interrupt comes, how much time does it take to run the corresponding service routine? So this is the event, the interrupt event, and then this is the interrupt service routine starts executing from here. The time that lapses between the occurrence of the event to the running of the interrupt service routine is the interrupt latency. Now later on we will see that there are various factors which result in a large interrupt latency in a traditional operating system, including the time to recognize the interrupt, and also if the we will see that the traditional operating systems, they mask the interrupts, and also if one ISR is running, so the ISR is non-preemptible, they can't have a recursive ISR, right? One ISR preempts another, etc., is not possible. So, under those situations, that is the time to recognize the interrupt and also for the interrupt routine to run, the time.
If a higher priority interrupt comes, then I think that ISR can be interrupted.
We will discuss more details of that the non-reentrant ISRs, we will discuss about that. So, this fixes the bound on the latency, interrupt latency, and we need this to be at least less than a few microseconds, and for sensitive applications might need the order of few nanoseconds. So, unless we have nested interrupt support, we need to perform bulk of the activities in a deferred procedure call. The interrupt service, the idea is that if the interrupt service routine takes long and nested interrupts are not possible, then we need to minimize the duration for which an ISR runs, and we will see that all operating systems, including the present Windows, Linux, etc., they use a deferred procedure call. The idea is that only do the very basic processing required as a ISR, and the rest of the task is queued as a deferred procedure call. A deferred procedure call is a substantial part of the ISR activity, which is executed just like a normal task, only the very crucial part of the ISR is carried out, and then the DPCs are queued as tasks. And not only we need preemptive kernel routines, but preemption during interrupt servicing as well. And we will also need some special support with respect to memory management. The traditional operating systems, we know that they support virtual memory and the memory protection features. Many of the embedded real-time operating systems, they do not really support virtual memory. The reason is that in presence of virtual memory, the worst case memory access time increases drastically. Why should it increase drastically? When you have virtual memory support, why should the worst case memory access time increase drastically compared to the average or the best case memory access time?
Because some pages are in the secondary.
Yes, page faults. So, memory access time will increase because they might be hard disk, like he says, page faults. So, that may be unacceptable for some embedded real-time embedded real-time tasks. Therefore, many of these, as we will see, commercial real-time operating systems, they do not support virtual memory. So, we will just stop here and we will continue from this point in the next class. Okay, thank you.